Hello everyone. This is the final video for section 7.3 and it will be on the exceptions to the octet rule. So we've been discussing Lewis structures and the octet rule in this section, and it should be mentioned that it isn't always true. So there are some exceptions and we want to talk about those exceptions just so that you recognize that those things are out there. It is possible to have, in some cases, molecules with an odd number of electrons. And when that happens, they'll have some unpaired electrons. And with unpaired electrons, it's impossible to have a complete valence electron shell. So that's the first one. So let's talk about that one, then we'll talk about the other two. When we have an odd number of electrons, we call that a free radical. It turns out that these type of molecules are typically fairly reactive because of having that odd number of electrons. So we aren't going to get too deep into this, but just whenever you notice an odd number of valence electrons, it will be something that is a free radical that therefore does not follow the octet rule. So there are a couple of examples of those right in here. We're not going to worry about the 5 steps for these ones that don't follow the octet rule. Just be aware that that is something that doesn't do that. We have some molecules that we say are electron deficient. What that means is they do not have 8 electrons on everything. They have less than that. And the two of the more common examples are shown here. This will often occur when you have a covalent bond that involves a metal, which is rare but does occur sometimes, as we're showing here, where you're just using the s electrons in the bonding and not the p electrons. Or you could have something where you have bonds to a highly electronegative element that does not want to share those with a double bond, as we're showing here. We could imagine rearranging this and making a double bond to make it satisfy the octet rule, but it turns out that doesn't happen. So we will very, very rarely see double bonds with fluorine. Some of the other halogens will sometimes form double bonds, but not fluorine because it has such a high electronegativity. And then boron is one that will often have this form because if you think back to its Lewis dot symbol, you had only 3 electrons to start with. So it's easy for it to basically form 3 bonds from there. And then so these are were the electron deficient, and then the final possibility are what we call hypervalent molecules. So these are molecules that have basically more than what you would expect, more than 8 electrons on the central atom, and we're showing a couple of examples of them here. And so what's going on here is that you have some amount of the d orbitals involved in these bonding, the bonding that goes on here. So empty d orbitals in the same shell that aren't yet involved in the bonding can be involved. And this is something we'll maybe get into a bit more detail on later in this module. Here are some more examples of some hypervalent ones that do actually still have lone pairs on the central atom. So we can see that this involves a noble gas in bonding. So with the some examples here, but the main thing you want to realize is that these things do exist. We'll see more of them in a later section, and being aware of that is all you need to know about these exceptions, is that exceptions do exist.